Hello, are you able to hear me?
Yes, sir. Good
Yes,
afternoon,
sir.
sir.
Okay, thank
Good
you.
afternoon, sir.
Very good afternoon. Yeah, yeah, yeah. Today we will discuss our topic is infrared spectroscopy. That is an FTIR spectroscopy. It means the Fourier transform infrared spectroscopy. Yes, yeah. Yeah, myself and Dr. Bhagwant Reddy. I am working as an assistant professor in Palamur University, the Department of Chemistry. Yeah. Let's discuss our topic. Introduction now. Uh, what is the what is the use for studying the FTR spectroscopy? I think you have studied in Gemini spectroscopy, IR, so and so and so and so and so. Yes, yeah. FTR spectroscopy is mainly used to detect or to identify the functional group, which functional group having the particular sample or compound. To identification of functional groups, FTR spectroscopy is mainly used for the to identification of functional group. The compound is having so and so functional group, so organic functional group, especially OH functional group is there, or acetate, carbonyl compounds, acids, esters, amines, uh, different functional groups. The which functional group is there, we can identify by using the FTIR spectroscopy. It is an FTIR spectroscopy is also an absorption spectroscopy. We have two types of spectroscopy. One is the absorption spectroscopy, another is the emission spectroscopy. The FTIR spectroscopy is an absorption spectroscopy. At the same time, UV, NMR, these are also absorption spectroscopy. Yeah. FT, uh, FTIR, IR, it can be provide a molecular fingerprint that can be used when the sample comparing samples. If two pure samples display the same IR spectrum, it can be argued that they can be same compound. IR or FTIR it does not provide is a detailed information or proof of molecular formula or structure. It can provide information on molecular fragments or especially is a functional group. Therefore, it is a very limited in scope and must be in conjugation with other techniques to provide is a more complete picture of the molecular structure. What is the requirement? The molecule is or the sample is if it is an IR active or not. We can determine by the structure of the molecules. If the structure of the molecule is having the dipole moment, having the permanent dipole moment or induced dipole moment, the sample is an IR active. What is basic criteria of the sample is IR active or IR active? The sample should be dipole moment. The sample should having the dipole moment or induced dipole moment. If the sample don't have a dipole moment, the sample is inactive for IR spectroscopy. Yes, yes. Are you able to hear?
Yes, sir.
Okay, thank you. We, uh, Here we have an IR. IR is FTR is we have the three kinds, three regions, three different wavelengths. One is the near IR and mid IR and far IR. The range of near IR is 12,000 to 12,500 to 4,000 nanometer wavelength region. The mid IR is 4,000 nanometers to 200 nanometers, and per IR is a 200 nanometers to 10 nanometers. Basically, our organic compounds, our functional group will get the peak at for mid IR. That is the range is the 4000 to 2200 nanometers. Mostly used nanometers. Yeah. What is the basic is the principle of IR spectroscopy? This the basic principle is IR when the IR light is passed through a sample or of an organic compound. Some of the frequencies are observed while others are transmitted. The plot of absorbance or transmittance versus and wave number gives an IR spectrum. In UV visible spectroscopy, the absorbance and wavelength is a graph in UV visible spectroscopy. But here, the transmittance versus is a wave number. Wave number is a graph. But conventionally, wave number versus and percentage of the transference is plotted. And molecules are made up of atoms linked by the chemical bonds. The movement of atoms and chemical bonds like spring and ball vibrations. Here we consider the between the two bonds. It is a it is in a spring here we have one atom. Blue color is a one atom, and green color is also one atom. The bond between these two bonds, it will be considered as like a string, like a string. Okay. These characteristic vibrations are called natural frequency of vibration. And look at here. These are the two types of bonds of vibration. One is the stretching bonds, another one is the stretching. The vibrations are oscillations along the line of the bond. We have two types of stretching. Here, this is the important. And but one is a symmetric stretching, and another one is a asymmetric stretching. We have two types of bond here: carbon and two different hydrogens. These different hydrogens are elongation towards the opposite direction. Elongation towards the opposite direction. This is a symmetric stretching. Here it's a green color carbon. With the carbon having the two hydrogens. These two hydrogens having the one carbon is towards the one hydrogen is bond is towards the carbon, and it means it is a compression, and it is the elongation. Another one is the elongation. Carbon to hydrogen. It is an elongation bond, and it is a compression. And these are the same side stretching. And first one is the opposite side stretching or stretching or compressions. That is a different sides. It we called as a symmetric stretching. Opposite side. Sorry, this one is the opposite. One is a compression, another one is a elongation. This is an asymmetric stretching, and this is an symmetric stretching. And also bending vibrations is also there, which is also an important because the vibrations or oscillations not along the line of the bond. For example, here we have carbon having the two hydrogens. Two hydrogens is bending towards the back side or front side. This hydrogen having the bending towards the back side, and this hydrogen having it towards the front side. It is a scissor bending, and this type of is rocking, and this type of is the switching, and this type of is the wagging. These two are in planes, and these two are the out of plane. This is in plane, and this is the out of planes. Yeah. Yeah. Infrared radiation is largely thermal energy. Then compared to the rotational energy, we have different types of energy levels. First, we have a molecule. If the molecule having some kind of energy, the molecule goes to the translation and compared to translation energy, we are giving us some more energy towards the molecule. The molecules goes to the rotations, and then after we have given some more energy. The molecule goes to the vibration. Then gaining the more amount of energy, giving the more amount of energy, the molecule goes to the electronic transition. These are the electronic energy levels. First, the translation energy, rotational energy, vibration energy, and electronic energy. We have four types of energies. Here is a infrared spectroscopy is having the vibrational energy. Yeah, the infrared radiation is largely thermal energy then compared to the rotation and translation. It reduces the stronger molecular vibrations in covalent bonds, which can be viewed as a spring holding together two masses of our atoms. Yeah, look at here. These are the two molecules, and this color, and this is an equilibrium state. Between these two bonds, the bond is like a spring, like a spring. If the two springs are elongation towards both different sides, different opposite sides, the molecule will be stretched, or it is in compressor. The molecule, the bond is in a compressor. The bond is a compressor. This is an example of vibration spectroscopy. Sorry, vibration spectroscopy or FTR spectroscopy. Both are safe. Both are safe. This is an FTR spectrum of some molecule, like it is a hexanoic acid. Hexanoic acid, some molecule. In this spectroscopy, we have a different kinds of functional groups. It is these functional groups having a particular range of peak. This, for example, where we have a carbonyl group, acid group. Acid group is there, CO. This acid group absorb a particular range of radiation only. Is approximately is a 1721. This is a OH stretching. Where we have a OH bonds. This molecule, the OH bond is appeared at 3000 something. We have a different range of radiations we will discuss later, and which functional group having which functional group having how much frequency nanometer we will discuss later. Just this is a brief. This is a FTR spectroscopy of different hexanoic acid molecule. We will discuss later. Yeah, we have two types of oscillation between the two bonds. For example, harmonic oscillation and anharmonic oscillation is also there. For example, a diatomic molecule. It may be assumed to be like an harmonic oscillator. It means it means the molecule can be stretched or compressed to any extent without breakage of the bond. An anharmonic oscillation can be characterized by frequency of vibration and energy. For example, we have one HCl is also there. HCl, one HCl molecule, one side is a H and another side is a Cl. Yes, when Cl molecule, Cl position is, for example, we have an HCl molecule, then chlorine molecule position is fixed and H molecule position is changed. H molecule position is changed towards away from the chlorine molecule. Then what happened? The energy of the elongation. Sorry, the energy is increases between the two molecules and chlorine and hydrogen. The equilibrium, the distance of the chlorine and hydrogen also increases. Yes, we have a molecule. So, it's okay. Hmm. Then what happened? Let Cl is fixed at some position and hydrogen moves towards or away from the position of the chlorine. Then what happened? The movement of an atom towards and away from its bonded atom raises the energies. Raises the energies. The energy of diatomic molecule as a function of interseparation can be the energy of diatomic molecule increases when the displacement from the equilibrium position increases. The compression and extension of bond may be linked to the behavior of a spring. For example, one hydrogen molecule, for example, where this is an Cl molecule and this is an hydrogen molecule. Yeah, when the position of the hydrogen is increases, like this increases, then what happens? The energy of the diatomic molecule increases. The displacement from equilibrium position increases. Like this is an equilibrium position. The energy increases. The displacement is also increases. Yes, elastic bond can be compared to the spring. Compared to the spring, the spring is which obeys the Hooke's law. The Hooke's law is where F is equal minus k into delta x minus k into delta x, where F is a restoring force, k is a force constant, k is a force constant. Delta x is the distances between the equilibrium and internuclear distances. Yeah. In the case of energy, in the case of in this case, the energy curve is parabolic and has a form of E is equal to 1 by 2 k into delta x square. Solving the above equation, the restoring force means the F restoring force and making the use of the Lagrange's equation, then we get that W is an oscillation of W oscillation is equal 1 by 2 pi root of k by mu in k by mu. This equation is a very important. This equation is very important. When W oscillation is equal to 1 by 2 pi is the root of k by mu. Where k is a proportion, uh, force constant, and mu is an induced mass. Mu is an induced mass. To convert this frequency to wave numbers, we must divide it by the velocity of the light. It can be expressed as is a W oscillation, W bar oscillation. Oscillation means it is a vibrational frequency in centimeters. Here it is the above equation it is an hertz. Equation is hertz. Here it is in centimeters. Here it is in hertz. Where we are not this. Here it is in centimeters. We are dividing by C. W oscillation is equal to 1 by 2 pi c root of k by mu, where k is a force constant and mu is an induced mass and c is the velocity, pi is a constant. Like all other molecular energies are quantized, vibrational energy is also quantized, and allowed vibrational vibration for any particular system may be calculated from the may be calculated from the Schrodinger equation for a simple harmonic oscillator. These turn out to be when E is equal to mu plus 1 by 2 into H W oscillation. This is in joules. Okay, it is a vibration energy is also a quantized energy. What does it mean by quantized? The quantized energy means each particular energy level having the fixed energy. Fixed energy. For example, first a ground state to first excited state, and second excited state, third excited state. These energies, these excited states having the fixed type of energies. The energy of the molecule in vibration energy levels can be calculated by using this formula. The formula is E is equal to mu plus 1 by 2 H W oscillation in joules. In joules, where E is the energy of the with vibration level. For example, first energy level or first vibration level, second vibration level, third vibration level, and mu is the vibrational quantum number, and W oscillation is the frequency with which the diatomic molecule is vibrating. Converting the spectroscopic units in centimeters, we can the E is equal U nu by Hc, that is equal mu plus 1 by 2 W H W oscillation by Hc. Hs will be cancelled. The E is equal mu plus 1 by 2 W bar oscillation in centimeters. This is the final equation of the energy. For example, when V is equal 0, V is equal means the ground state of the vibrational energy. The energy of the ground station is 1 by 2 mu bar Hc. For example, yeah, look at here, where W bar oscillation is vibration frequency expressed in centimeters. If V is equal 0, the energy level is the lowest energy level. When V is equal 0, the above equation reduced to EV is equal to 0 plus 1 by 2 W oscillation. When EV is equal to 1 by 2 W oscillation, and it is known as a 0 point energy. 0 point energy. This is the 0 point energy. When V is equal to the quantum number, V is equal vibrational quantum number, V is equal to 0. The energy of the molecule in ground state, that is equal to EV is equal to 1 by 2 W bar oscillation. This energy is known as a 0 point energy. It is an important, for example, in your even entrance point of view is also it is an important. V is equal to 0, then E is equal to 1 by 2 W bar oscillation. This we call as is a 0 point energy. Yeah, the existence of the 0 point energy is in accordance with the quantum mechanics. With this also indicates that the molecule are in constant motion even at 0 kelvins. Even at 0 kelvins. Even it means even 0 kelvins, the molecule or the sample, the atoms of the atoms having the same energy, some energy, even at 0 kelvins. Even at that means even at 0 kelvins, the molecule having the some energy. The energy is called as a 0 point energy. At the same, the rotational energy is also, if J is 0, the energy is also 0 in the rotational spectroscopy. But in FTR spectroscopy, vibration spectroscopy, if the vibration quantum number is 0, the energy should not be 0. The energy is equal to 1 by 2 W bar oscillation. That we call as a 0 point energy. What is the selection rules for vibration spectra? First one, molecule having the dipole moment. The molecule having the dipole moment. If the molecule don't have a dipole moment, the molecule is not active in FTIR spectroscopy. The molecule is not active in FTIR spectroscopy. For example, CO2 is there. CO2. CO means O double bond C double bond O. The molecule have the CO2 is not having the dipole moment. It means the CO2 is an inactive for FTIR spectroscopy. The molecule should having the dipole moment or induced dipole moment. Okay. Then next selection rule is when dV delta V is equal plus or minus 1. Plus or minus 1. Applying the selection rules to the diatomic molecule, we get the translation such as when V is equal 0, V is equal 0 to, it means V ground state to V is equal 1. 1 means it's a first excited state. Or V is equal to 1 to V is equal to 2. V is equal to V is equal to 3. For example, look at here, then V is equal to 0. 0 to 1. This is the ground state of the vibrational energy, and this is the first excited state. And second excited, P is equal to second excited state, and V is equal to third excited state. The transitions should be occur. The only difference is only one. V is equal V0 to V1, V1 to V2, or V2 to V3. Not for V0 to V2 or V1 to V3. It's not occur. It's occur only the plus or minus 1 only. Okay, this is the selection rules for FTIR spectroscopy. Then calculation of force constant. It is an important. It will come in problem also. And W oscillations. W bar oscillation is equal. Earlier we have discussed this equation. W bar oscillation is equal 1 by 2 pi c root of k mu. If it is the removing of the root, we can square here, and W bar oscillation square is equal 1 by 4 pi square c square into k by mu. When k is equal 4 pi square c square mu and W bar oscillation. When where k is a force constant and c is a velocity and mu is an induced mass. Mu is an induced mass. Look at one example here. Calculate the force constant for hydrogen fluoride, whose vibration frequency is 4138.5 centimeters inverse. Vibration frequency means W bar oscillations. Yes. Then what is the formula for calculating the force constant? Where k is equal 4 pi square c square mu into W bar oscillation square. Given that 4 pi square is a constant and W bar oscillation is given in problem, that is a 4138.5 centimeters, and the mu is an induced mass. What is the induced mass formula? M1 into M2 by M1 plus M2 into 1 by N. N is an Avogadro number. That is the mass of the which hydrogen and fluorine. What is the mass of the hydrogen and mass of the fluorine? What is the mass? 1. What is the mass of the hydrogen is 1 and mass of the fluorine is 19. Yes, is 1 into 19 by 1 plus 19 into 1 by N. That Avogadro numbers, just 6.23 into 10 to the power of 23 in grams. Yeah, that is a 0.95 by 6.02 into 10 to the power of 23. The K value is 39.47 into 3 into 10 to the power of 10 into square into something. This is the force constant is equal. Calculating this simplification this equation. Finally, we get K is equal to 9.5 into 9.5 into 10 to the power of 5 grams per centimeter square. This is the units of the force constant. Force constant in some simple molecule. Here, look at here, when hydrogen fluoride and HCl and HBr and HI. These three are the same group. Molecules having the same groups. Yes, same group. The difference is the Electronegativity differences. These four having the same group. These four having the same group, but hydrogen is the same. Then top to bottom, the electronegativity of the top to bottom is differences. Then compared to HF, when fluorine having the more electronegativity than compared to the fluorine. When chlorine having the more electronegativity than compared to the iodine. Yes, at the same time, the force constant is also decreases from top to bottom. Look at here. The force constant is also, the frequency also decreases. The force constant is also decreases. Look at here, for hydrogen fluoride, the force constant is a 9.7. Then HCl is 4.8 and HBr is a 4.1 and hydrogen iodide is and 3.2. The electronegativity is decreases. The force constant is also decreases. Simple. The electronegativity is decreases. Here force constant is also decreases. Why it is decreases? Simple logic. When the bond between hydrogen and fluorine is very strong, then compared to the chlorine and hydrogen and chlorine, hydrogen and hydrogen and bromine, and hydrogen and iodide. If a bond is very strong, if these two bond is very strong, the difference between these two bonds is very strong. Then K, the force constant is also very high. It means the bond break between the hydrogen and chlorine. The the hydrogen having the small size is the fluorine also having the small size. But the fluorine is high electronegativity. High electronegativity means the distance, the bond length between the hydrogen and fluorine is having the is a very small. Is very small than compared to the HCl, HBr, and HF. If the bond is very small, the bond distance is very small, the force constant is also very high. If the bond distance between where compared to this one, hydrogen and chlorine, compared to hydrogen and fluorine, the hydrogen and chlorine is also uh, little length, little bit length. Then compared to the hydrogen and bromine, it is a very length, and hydrogen and bromine, it is a very length because of simple when iodine having the large size, hydrogen having the very small size. These two, the polarization is also differences. The bond break between these two is very easily. The force constant is also the required energy for break these two bonds is very little bit energy. If the energy is required energy is little, the force constant is also small. For example, compare these hydrogen and chlorine. These two are having the same size. For example, not the same size. The bond break between these two is very required energy is very high. Required energy is very high. The force constant is also uh, uh, heavy, large. The force constant is also large. Look at here. This is a 9.7, and compared to this is the force constant is also decreases 4.8 because of the energy difference the bond, the required energy from these two to break the bond between these two is very less than compared to the hydrogen fluoride. That's why the force constant is also decreases. This is a simple logic. The force constant values for the double bond and triple bonds, except hydrogen fluoride, it can be proportional to the calculated for the force constant. For example, we have a single bonds. Single bonds required energy is very less. We have a double bonds and triple bonds. The bond break between the double bonds, then compared to the single bond, the double bond having the double bond having a more energy. And this is an anharmonic oscillation. We have two types of harmonic oscillations. One, two types of oscillations. One is a harmonic oscillations, another one is a anharmonic oscillations. Look at here, it is a very yeah yeah. Here, here it's a red color balls. These balls are one atom, and this balls is also one atom. The between these two bonds, we have a bond. The bond is a string, like a string. It increases, the energy is increases, the bond length is also increases. Energy is increases, the bond length also increases. That is a harmonic oscillation. For example, look at here, the green color light it is indicates is a harmonic oscillation. Harmonic oscillation. Look at here, the energy V is equal 0, little bit energy, and V is equal 1. Right? And its elongation occur. And elongation occurs. And the distance between these two bonds are increases. Elongation. Like here, the energy increases, the bond length is also increases. Here, the bond length is very small, and this is the bond length is increases. Energy is also energy. This is the energy, and energy is also increases. Energy increases, bond length increases. Energy increases, bond length increases. Energy increases, bond length increases. This is an harmonic oscillation. Harmonic oscillation, but it is not real in practical. Just it is a theoretical assumption only. Because the comparative is a practical assumption is the practical, energy increases, bond length increases, energy increases, bond length increases. It is a some extent only. The bond will be broke at some particular energy levels. The some particular energy levels. Where look at here, when V is equal to 6, this bond will be broken. Bond will be broke here. Bond will be broke here. This is an harmonic oscillation, anharmonic oscillation. Anharmonic oscillations. The real molecules do not follow law of the real molecules do not follow law of simple harmonic motions. They do not obey the Hooke's law at all internuclear separations. In some of the real molecules, small compressions or elongations are preferably elastic and obeys a simple harmonic motions. But for longer compressions or elongation, they may they deviate. Experimentally, it is observed that the molecule is stretched over the 10% of its bond length. The molecules dissociates into atoms. The bond will be broken out, or atoms or ions. The energy of a real molecule as a function of internuclear separation is given by the Morse curve. Morse curve. Morse curve. This is a Morse curve. Yes, yeah, it's a blue color is a Morse curve. It looks like it's a Morse. This is a Morse curve. Bond will be broken at certain extent. A purely empirical compression, a purely empirical expansion, which fits this curve, to a good approximation was derived by the PM Morse, and is called as a Morse function, and is called as a Morse function. The energy is given by this energy is uh, for an harmonic oscillation. The previous energy is harmonic oscillation, and this equation is for anharmonic oscillations energy, where E is equal to d eq into 1 minus exponential a into r equilibrium minus r of square, where a is the constant for particular molecule and dq is the dissociation energy. Substituting equation 1 into the Schrodinger wave equations, one one can get the vibrational energy for anharmonic oscillation. It is given by an EQ, E, where V is the vibrational quantum number. EV is equal to nu plus 1 by 2 W bar oscillation minus V plus 1 by 2 square WEXE into centimeters. This equation for anharmonic molecules. Where previously equation, what is equation? EQ is equal to only this one. EQ is equal to V plus 1 by 2 WE, W oscillation. There is this equation for harmonic oscillation and this equation for anharmonic oscillations. Where Xe is the uh, anharmonicity constant, which is in the order of
I think on
0.001 and has a no units. Yeah, look at it. As a simple harmonic oscillation, a simple harmonic motion is a type of periodic motion where the restoring force
అయినా నేను
is the
నిన్న కొనమన్నాను కదా ఇవాళ వచ్చినప్పుడు కొనిసి తేవచ్చు కదా తేవు.
restoring force is directly proportional to the displacement. Anharmonicity is the deviation of a system from the being an harmonic oscillator. A uh, oscillator that is not oscillating in a simple harmonic motions. Yeah, this is a very important examination also. Yeah. We have a different bonds, different kinds of transitions, and different bonds is there. That is the fundamental bonds and overtones and hot bonds. We have two bonds. One is the fundamental bonds and overtones. What is the fundamental bonds? What is the fundamental bond? The transition from, we have a difference. This is the energy anharmonicity, the Morse curve, uh, where the zero is the indication is the ground state of the molecule, and one is the indication of is the first excited state, and two is the indication is the second excited state, which is the third excited state, and fourth excited state. But then what happens whenever we are giving to some energy to the molecule may be absorb the energy, the molecule goes to the higher energy levels. Yes, yeah. For example, the transitions from then V0 to this is the V0. This is an V0. This is an V0. The state is the ground state. The transition from V0 to V1. V0 to V1. The transition between V0 to V1 and the bond appeared by the transition is known as a fundamental bonds. Fundamental bonds. The transition from V0 to V1. Okay. Then the transitions from this is also the selection rules also. What is the selection rules? Delta V is equal plus or minus 1. The fundamental bonds is that is the transition according to the selection rules, and delta V is equal is a plus or minus 1. The transition is said to be a fundamental transition. Then first voter. What does it mean by first voter? Look at here. Then it is a represents a double jump by the molecule from V0 to V2. V0 to V2. From molecule from V0 to V2. This transition V0 to V2. And this bond occur with a small intensity. This bond is known as a first overtone bond. First overtone bond. The transitions from V0 to V2. The transitions, the transition between V0 to V1 and the bond appeared by this transition is known as a first overtone. First overtone. What does it mean by second overtone? The transitions from V0 to V2, sorry, V3, and the bond appeared by this transition is known as a second overtone. What is the third overtone? The transitions from V0 to V4. Transitions from V0 to V4, and the bond appeared by this transition is known as a third overtone. It is an exam point of view. It is also very important. What is the fundamental bonds? First, to define the fundamental bonds: overtone, first overtone, second overtone, third overtone. The transitions from V0 to V1 we call as a fundamental bonds, fundamental transitions. The bond appeared by this transition is known as fundamental bonds. What is the first overtone? The transitions from V0 to V2, and the bond appeared by this transition is known as a first overtone. Yeah. The fundamental bonds and the first overtone and second overtone. It, in the overtones, the selection rules also different compared to the fundamental rules. The fundamental rules it obeys the fundamental bonds in the selection rule is delta V is equal plus or minus 1. In the first overtone, the delta V is equal plus or minus 2. And the second overtone, the delta V is equal plus or minus 3. The selection rules is different from compared to the fundamental bonds and overtones. Hard bonds. Hard bonds. The transitions from V0 to higher levels are not observed unless the temperature of the sample is high. This is due to the fact that the population at V is equal to 1 level is negligible at room temperature. It becomes appreciable at higher temperature. These transitions are known as hard bonds as they appear only at higher temperatures. The intensities of the hard bonds are usually very weak and become more intense in increasing in the temperature of the samples. This means the transitions here, look at here, the transitions from the transition started at minimum is V0 to V1, V2, V3, V4. In hard bonds, the transition is started occur from V1, minimum least energy level is V1 or V2. V1 to V2 or V1 to V3 or V2 to V3 or V3 to V4. These kind of bonds will appear at higher temperature only. Okay? Higher temperature only. That is a hard bonds. Yeah, next one is vibrational rotation spectra of diatomic molecules. According to the Bohr opinion, approximations, the total energy of the molecule is given by. The total energy of the molecule is E total is equal to E electronic plus E vibrational and E rotational and also E translational. The translational energy is it is a not quantized energy. That's why we are not considering here that energy. We can consider only these three energies, that is the electronic, vibrational, and rotational energies. Yeah. Since we have considered vibrational and rotational spectra, the above equation can be modified. Then E total is equal to E vibrational plus E rotational. Inserting the equations for E vibrational plus E rotational and E vibrational rotational and E J means where J is a rotational quantum number here where, where J is a rotational quantum number and V is the vibrational quantum number and this is the energy for rotational energy. This is a rotational energy and this is a vibrational energy. This equation has we have discussed in previous. This energy will come from rotational spectroscopy where we are adding two energies. Then E total is equal to E vibrational plus E rotational. This is a rotational and this is a vibrational energies. Yeah, the relative here diagram, the relative energy levels diagram for the first two vibrational energy levels is shown below. That is where, yeah, this is the energy levels, vibrational, two different energy levels. This is an V0. And this is an V0 ground state vibrational energy levels. And this is an first excitation of vibration energy levels. We have an in vibration levels, the vibration each vibrational energy levels having the different number of rotational energy levels. Each vibrational energy levels having the different number of rotational energy levels. Okay, that's why where V is equal 0. In the V is equal 0, we have a more more number of rotational energy levels. That is a then V is equal J is equal 0 and J is equal 1, J is equal 2, J is equal to so and so, so and so, so and so. Each here, look at here, when V is equal to 1, this is the first excitation of vibrational energy levels. Each vibration level having the more number of rotational energy levels. Yes, then V is equal J is equal to 0, J is equal to 1, J is equal to 2, J is equal to different. We have a different number of rotational energy levels. Each vibrational energy level is accompanied by more number of rotational energy levels. Okay, look at here. The transitions from J is equal to 0 to J is equal to 0. Look at here. The molecule started here. J is equal to 0. The molecule ended from J is equal to 0. J is equal to 0 to J is equal to 0. For example, where the molecule started here, J is equal to 1. The transitions from J is equal to 1 to J is equal to 0. J is equal to 1 to J is equal to 0. The difference is delta J is equal to minus 1. 1 to 0. Okay, look at here. The J is equal to 2 to J is equal to 1. 2 to 1 minus 1. Difference is minus 1. Here J is equal to 3 to J is equal to 3 to 2. Same transition, look at here. When J is equal to 1 to J is equal to 2. J is equal to 1 to 2. J is equal to 2 to 3. J is equal to 3 to 4. The difference is a plus 1. Delta J is equal to plus 1. Where delta J is equal to minus 1. If the difference is delta J is equal to minus 1, the bond is the P branch. The bond is the P branch. When J is equal to plus 1, that is an R branch. There is no difference. J is equal delta J is equal 0. If the delta J is equal 0, it means the transitions from J is equal 0 to 0 J is equal to 1 to 1, J is equal to 2. That we call as a Q branch. Q branch. J is equal to 0, it is a Q branch. If the J is equal minus delta J is equal to minus 1, that is a P branch. If the delta J is equal to plus 1, that is an R branch. Signal will be like this. This is a P branch and this is a Q branch. The middle one is the delta J is equal to 0, that is a Q branch. This is the energy difference between the delta J is equal to 0. The energy is difference is 2 GB, 2B and J plus 1 in centimeters or meters. This equation will come in rotation spectroscopy also. Yeah, this is also very important. This is applications of spectroscopy. It is very important. For example, vibrations of polyatomic molecules. Vibrations of is a polyatomic molecule. The IR spectra of polyatomic molecules may exhibit more than one vibration absorption peaks. More than one absorption vibration peaks. The number of these bonds is correspond to the number of fundamental vibrations in the molecule, which can be calculated from the degree of freedom of the molecule. For example, the number of vibrations. This is a formula. This formula is very important. Is the number of vibrations. Number of vibrations 3n minus 5 per linear molecule. We have a molecule structure. Molecule structure, for example, with CO2. CO2 is a linear molecular structure. The formula is 3n minus 5. And non-linear molecule, for example, H2O. H2O is a non-linear molecule. The formula is 3n minus 6. 3n minus 6. Where n is a number of atoms. Number of atoms in the molecule. Number of atoms in the molecule. Yeah. Look at here. When, for example, H2O molecule. In H2O molecule, in H2O molecules, how many where two hydrogens is there and one oxygen is there. Total 2 plus 1, 3. Total number of molecules is 3, where n is equal to 3. For this is the H2O is a non-linear molecule. Yes, where H2O is a non-linear molecule. For non-linear molecule, the formula is 3n minus 6. 3n minus 6, where n is equal to 3. Substitute the n value in this equation, then we will get then 3 into 3 minus 6. That is a 9 minus 6. We have a 3 types of bonds. This is the 3. This is the fundamental bonds for three fundamental bonds for H2O molecules. And CO2. CO2. How many molecules is there? 3 molecules, where n is equal to 3. This is the CO2 is a linear molecule. Yes, linear molecule. What is the formula for linear molecule? 3n minus 5. Three n minus 5, where n is equal to 3n minus 5. N is equal to 3. 3 into 3
Sir,
minus 5. Yes,
H2O,
please.
H2O it is only two, no, sir. Answer is coming through.
No. H2O, two hydrogens and one oxygen. Total three molecules, where n is equal to 3.
Then CO2 is
CO2 is also 3.
3 only, no, sir.
Two
One is
oxygens.
linear and other one is non-linear. So
Yes,
then
but
by the formula we can get that only.
yes, this is a linear molecule. CO2 is a linear molecule. The formula is different. 3n minus 5. This is an 3n minus 6.
Okay. Yes,
Yeah,
sir, we are getting number of vibrations 3.
different. For
Okay.
H2O will get the three vibrations, and CO2 will get the 4 vibrations.
How we are getting 4 vibrations, sir? 1, 2, 3 only, no, sir.
No, formula is different. For 3n minus 5 for linear molecule, 3n minus 6 for non-linear molecule. Where H2O is a non-linear molecule and CO2 is a linear molecule. So both the formula is different. A 3n minus 6, a 3n minus 5.
Okay, sir.
Yeah, 9 minus 6. 9 minus 6 is a 3. 9 minus 5 is a 4.
Okay, sir.
Okay. Look at another example. Yeah. C2H6, ethane molecules. Where how many numbers is there? How many molecules is there? 2 carbon molecules and 6 hydrogen molecules. Total 8 molecules.
Eight
Yes.
molecules.
Yeah. What is it? This is a linear molecule or non-linear molecule? It is a non-linear structure,
On
non-linear molecules. What is the non-linear molecule for formula? 3n
3n
minus
minus 6,
6. Where n is
where
equal
n
to
plus 8,
8. 3 into 8 minus 6. 24
24
minus
minus 6.
6.
It
Total
will get
vibrations is 18. Yeah.
18.
Yeah. This is the vibrations of as a polyatomic molecule. Just a very simple structure, simple formula. It may come enter even entrance also. CSR, whatever it is set to entrance, it will also come. It will come. Yeah. Next. Next is a combination bonds and different combination bonds and difference bonds and Fermi resonance. The Fermi resonance is important for your short question. For short questions, Fermi resonance is important. What is the combination bonds? Let us discuss. The combination of bonds are weak intensity and the and occur when two fundamental bonds couple to give bonds at V1 plus V2 or V1 minus V2. V1 plus V2. For example, this is a we have V0, V1 and V3. The transitions from V0 to V1 and transition from V1 to V2. These two bonds, the combination of these two bonds will get one bond. For example, this is a weak bond like this and this is also weak bond like this. The combination of these two bonds will get like higher intensity. This type of weak bonds we call as a combination bonds. Okay. Two vibration frequencies V1 and V2 in the molecule coupled to give a rise to a new infrared active frequency. This bond in the sum of the two interacting bonds, that is a V combination bonds, V1 plus V2. The combination bonds are observed when more than two or more fundamental vibrations are excited simultaneously. This is a condition for combination bonds. And Fermi resonance, it is important for your short questions. When a vibration coupled with an overtone, fundamental vibration coupled with an overtone are combination bonds. When a fundamental bond couples with overtones are combination bonds. The coupled vibration is called as a Fermi resonance. The Fermi resonance is often observed in carbonyl compounds. Fermi resonance results in the splitting of two vibrational bonds that have nearly the same energy. and symmetry, same energy and same symmetry in both the IR and Raman spectroscopies. The two bonds are usually a fundamental vibrations and either an overtone or combination bonds. For example, look at here. This is a vibration bond. This is an one bond. It's a fundamental bond. The higher intensity is a fundamental bond, and this is a lower intensity is an overtone. The combination of these fundamental bond and overtone bond, it will give the two bonds, two different intensities bond. The here the fundamental bond intensity has decreases. Here, the overtone bond intensity has increases. This type of interaction we call as is a resonance. That we call as is a Fermi resonance. A fundamental bond intensity is decreases. A overtone bond intensity has increases. By combining by these two bonds, these type of interactions or these type of resonance we call it is a Fermi resonance. Yeah. Next one is the concept of group frequencies. We have two types of frequencies, and then one is vibrations. One is the skeletal vibrations and group vibrations. For example, fragments, fragments such as this type of carbon, 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 or CO, 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 or benzene, etc., will give the skeletal vibrations where all the atoms are displaced to the same extent. Most of the skeletal vibrations falls in the range of 1400 to 700 centimeters inverse. The range which is known as a fingerprint region. What is the fingerprint region? The range between the range is a 1400 to 1700 centimeters. We call it is a fingerprint region. The next one is the group frequencies. The group vibrations are the characteristics of groups and are usually independent of the structure of the molecule. Structure of the molecule. These vibrations falls fall well above the and below the fingerprint region, well above or below the fingerprint region. Group vibrations, light atoms at internal or terminal groups will occur at higher wave number, while those of heavy atoms occurs at lower wave number. Characteristic of the group frequency. For example, look at here. Yeah, this is a group. When OH group is there, then OH group is there. OH group will occur at 3640 to 3600. If the peak will occur at 3600, the molecule should having the OH group or NH2 group. If the molecule having the NH2 group, the peak will be appear at 3400 centimeters, or the molecule will having the
Sir, Fermi band, you said fundamental vibration coupled with an
triple
overtone.
bond CH. This CH, the carbon is a triple bond. So these values. Sorry. Yes, please.
Sir, Fermi band, you said fundamental vibration coupled with an overtone or combination band. Sir, what is combination band?
Combination bond means like V1 to V1 plus V2 bonds. Later we earlier we had discussed. Yeah, look at here.
Acha, okay, sir.
Yeah, this one V1 plus V2 bonds or V1 minus V2 bonds.
Okay, okay, sir. Okay.
Yeah, if the carbon hydrogen bonds here, the bonds is look at here the carbon double bond CH. This bond, if the molecule having this type of bonds, the peak will appear at 3060, or carbon double bond carbon CH2 molecules. The peak will appear at 3030, or carbon having the single bond. Carbon hydrogen bond will appear at 2970 with asymmetric stretching. If the symmetric stretching is there, 2870. Yes. CH2. CH2 bond is there. If the molecule having the CH2 bond, the peak will appear at 2930. Not exactly 5-10 nanometers approximately, or above or below. The molecule having the cyanide, if the molecule having the cyanide group is there, the molecule should be having the peak at 2250. If the molecule having the carbon-carbon triple bonds, the peak should be appear at 2220 or 2210, 10 nanometers above or below. It's not exact. If the molecule having the CO group, C double bond O group, the peak will be appear at 1750 to 1600. If the C double bond C means if the molecule may be ester or acids or carbonyl compounds or amides, whatever it is. If the molecule having the C double bond C, the peak will appear 1650. Or the molecule having the C double bond N, the peak will appear 1600. You should be by heart these values. If the molecule having the C single bond C, the peak will be 1200 to 1000. Or C double bond N, or C single bond N, C single bond O. The peak will be 1200 to 1000. The C double bond sulfur, yes, the peak will be 1100. CF 1050 and Cl 1725, Br 1650 and Ci 500. Because of here the frequency decreases, wave number is decreases due to the decreasing in the electronegativity. Force constant is also decreases from top to chlorine to iodine. The wave number is also decreases. Yeah, this is also very important exam point of view. And structural and stereochemical effects on the absorption pattern in carbonyl group. Carbonyl group switching frequency occur in the range 1750 to 1600 centimeters. Yes, depending upon the nature of the substituent group, its intensity is high. The position of the carbonyl switching frequency in various compounds is listed below. For example, saturated aldehyde is there. The peak will be appear at 1740 to 1720. Or aryl aldehydes. Aryl aldehydes is there. The peak will be 1715 to 1695. The frequency has decreases. With alpha halo aldehydes. The peak intensity has increases because then what happened? Look at here. There is a simple concept. For example, this is an saturated aldehyde. The peak appeared at 1740. Yes. Then aryl aldehydes. The peak frequency has decreases. Wave number has decreases. 1740 is there. 1750 is there. Why decreases? Because of where aryl group is electron donating group to the aldehydes. Yes. If the electron donating group is there, the force constant has decreases. The force constant decreases, the frequency, the wave number is also decreases. So for example, we have in the alpha halo aldehydes where halogen groups is there. Halogen, what is the main nature of the halogens? Halogens is a more electronegative groups than compared to the other groups. Yes, then more electronegativity means electronegativity means attraction of electrons to the neighboring groups, neighboring atoms. Then what happens? The more electronegativity is adjacent to the carbonyl group, then the force constant is also increases. The force constant increases, the wave number is also increases. It means the electron attracting groups. Halogen means electron attracting groups. Here aryl is electron donating group. If the compound having the electron donating group, the frequency, the wave number has decreases. If the compound having the electron withdrawing group, the frequency is increases. The wave number is increases. This is a neutral. This is saturated aldehydes, and this is an electron donating aldehyde, and this is an electron withdrawing aldehydes. If the donating aldehyde is there, the frequency, the wave number has decreases. Yes, if the electron withdrawing groups is there, the wave number has increases. The simple concept. Same, same. Hydrogen being a more electronegative with withdrawing some electron density from the carbon with which it is bonded, the carbon becomes electron deficient, and draws some electron density from anti-orbitals of CO. This results increasing in the bond order CO. Therefore, the absorption in halo hydrogens shift to the longer volume. Where bond order increases means the force constant is also increases. If the force constant increases, the bond order also increases. The position of the carbonyl stretching frequency in alpha halo aldehyde is also influenced by the stereochemistry of X with respect to the carbonyl group. For example, another example, we have a ketones. We have another carbonyl group, that is the ketones. It is a saturated ketone. The saturated ketone appear at 1725 to 1705. Yes, it's a molecule having this is a saturated group. And this alkyl ketones. Alkyl ketone means the molecule having the electron donating groups. Yes, if the molecule having the electron donating groups, the wave number is also decreases. It is an electron donating group. Alkyl is an electron donating group. If you look at here, then alpha haloketones, where halogens is an electron withdrawing group. If the molecule having electron withdrawing group, the frequency, the wave number is also increases. If the molecule, simple example, simple concept, if the molecule having the electron donating group, the wave number decreases. If the molecule having the electron withdrawing group, the wave number is increases. Same concept in acids, also same concept. The acids, saturated carbonyl acids, is appeared at 1815 to 1719. Aryl are alpha beta unsaturated. The frequency is decreases because of where aryl is a electron donating groups. Electron donating group. And another example, saturated aryl and alpha beta unsaturated. 1750.
Sir, we have to by heart these peaks.
No, no need to, but you should by heart minimum at least saturated carbonyl group 1815 to 1. You have to by heart one value. If the electron donating group is there, you can add, we can less some number, lower wave number. If the electron withdrawing group is there, higher number. Not exactly, not 10 pi, exactly 10 nanometers. But you should by heart basic saturated carbonyl groups are saturated. This value you should by heart. This with Vihana OH group should be by heart. These values. This value you should by heart. If the compound is donating group, less wave number. If compound is electron withdrawing group, more wave number. acid anhydride, saturated acid 1850 to 1800. If the aryl anhydride is there, frequency has decreases, where aryl means electron donating group 1830 to 1780. Yeah, this is the year, and we have another part. Same structural and chemical, stereochemical effects on the absorption patterns in carbonyl groups. In carbonyl groups, look at here, very simple. A saturated carbonyl aldehyde is there. Saturated aldehyde is there. What is the peak range? 1740 to 1720. Okay. If the aryl compound is there, aryl aldehydes is there, then frequency has decreases from 1740 to 1715. The alpha halo aldehydes frequency has increases. One minute, just wait. Okay, are you there? Hello.
Hello, sir.
Hello. Yeah.
Can't hear, sir.
Yes, sir.
Okay. Yeah.
Yes,
Next our
sir.
topic. Yeah. Thank you. Yeah. Next our topic is a cis trans isomerism. How we differentiate cis and trans isomerism. For example, we have the stretching frequencies of CC occurs in the region 1680 to 1620 centimeters as a weak bond. If the substituents are present and the carbons are symmetrically placed, the stretching vibrations becomes very weak, will not be observed. The CC stretching vibrations cannot be used as a diagnostic to distinguish cis and trans isomer. For example, simple is we have a simple. If the CH vibrations, C double bond C H type of fragments, however, are dependent on the type of the substituent present on the double bond carbons. For instance, CH VAG mode or trans isomer give the strong bond around at 1980 or sorry 965 centimeters. While the CH VAG we have for the CH VAG mode of cis isomer gives medium to the strong bond around 1730 to 650 centimeters. The following we have misplaced. This is not correct.
Sir, excuse me. This trans
Yes,
isomerism. Repeat it, sir.
yeah, wait. I think one picture has missed. Wait 1 minute.
Can't audible, sir.
Sir, no idea. Audio, sir.
Sir, are you there?
Only we are there.
Sir left.
You have completed assignment.
No. Maybe some technical issue, I think.
Meeting time is over now.
Sir is there or left?
Sir
Any
left out.
co-host is there?